a team of researchers from Boston College has published an article in Nature Communications marking the discovery of a novel metallic specimen where electrons have fluid-like dynamics. Experimenting with the synthesis of niobium and germanium, they discovered that a strong interaction between electrons and phonons alters the transport of electrons from the particle-like to fluid-like regime. Phonon refers to an elementary vibrational motion in which a lattice of atoms or molecules uniformly oscillates at a single frequency. Thus, they can be thought of as quantized sound waves. According to the lead researcher, Assistant Professor Tafti, electrons are scattered by phonons, which leads to the usual diffusive motion of electrons in metals. A new theory shows that when electrons strongly interact with phonons, they will form a united electron-phonon liquid. This novel liquid will flow inside the metal exactly in the same way as water flows in a pipe. It is worth noting that water molecules flow with a fluid continuum, obeying the laws of hydrodynamics, while electrons flow as individual particles and diffuse inside metals as they get scattered by lattice vibrations. Furthermore, the researchers carried out 3 experiments that showed different results. Electrical resistivity measurements showed a higher than expected mass for electrons. Raman scattering showed a change of behavior in the vibration of the niobium and germanium crystal due to the special flow of electrons, and X-ray diffraction revealed the crystal structure of the material. To further probe into the mass of electrons, the researchers used a specific technique called quantum oscillations and found the mass of electrons in all trajectories to be 3 times larger than expected. Though surprising in a simple metal, this is because electrons interact with phonons strongly. They are dragged by the lattice and it appears as if they have gained mass and become heavy. The team states that their next avenue is to find other materials in this hydrodynamic regime through this phenomenon, controlling the hydrodynamic fluid of electrons in such materials and engineering new electronic devices. Simply put, skin electronics are thin, flexible electronics that can be mounted onto the skin. Though it may sound like something out of science fiction, it is anticipated that soon such devices can serve as next-generation devices with a wide range of applications such as health monitoring, health diagnosis, virtual reality, and human-machine interface. One challenge that the researchers have faced in this field is that skin electronics require stretchable conductors that satisfy metal-like conductivity, high stretchability, ultra-thin thickness, and ease of patternability. However, achieving these properties simultaneously is extremely difficult. In this regard, researchers at the Institute for Basic Science, South Korea have made a significant leap. They have developed a new float assembly method to fabricate a nanomembrane that satisfies all these requirements simultaneously. The exceptional material properties are attributed to its unique cross-sectional structure, in which a monolayer of compactly assembled nanomaterials is partially embedded in an ultra-thin elastomer membrane. This new float assembly method takes advantage of the Marangoni effect, which occurs in 2 liquid phases with different surface tensions. When there is a gradient in surface tension, a Marangoni flow is generated away from the region with lower surface tension towards the region with higher surface tension. This means that dropping a liquid with lower surface tension on the water surface lowers the surface tension locally, and the resulting Marangoni flow causes the dropped liquid to spread thinly across the surface of the water. Keeping the Marangoni effect in mind, the researchers dropped a mixture of metal nanowires and rubber dissolved in toluene and ethanol on the surface of the water. The toluene rubber phase remained above the water due to its hydrophobic property, while the nanowires ended up on the interface between the water and toluene phases. The ethanol within the solution mixed with the water to lower the local surface tension, which generated Marangoni flow that propagated outward and prevented the aggregation of the nanowires. This assembled the nanomaterials into a monolayer at the interface between water and a very thin rubber solvent film. Next, they dropped the surfactant to generate a second wave of Marangoni flow, which tightly compacted the nanowires. Finally, the toluene evaporated, and a nanomembrane with the required unique structure was achieved, having high stretchability of over 1000 degrees while a thickness of only 250 nanometers and metal-like conductivity over 100,000 Siemens per centimeter. According to the researchers, this nanomembrane can serve as a new platform material for skin electronics and opens a path to new research fields involving various types of nanomembranes with different functions. Speaking of skin electronics, researchers from the Rice University and Brown School of Engineering have made a shirt that can monitor the wearer's heart rate. The researchers sewed a zigzag pattern of nanotube fibers into regular athletic wear and are washable, comfortable, and far less likely to break when a body is in motion. The fibers upon contact act as electrodes to connect electronics like Bluetooth transmitters to relay data to a smartphone or a Holter monitor. Goodbye uncomfortable chest straps. Recently, astronomers have found dramatic evidence of a black hole or a neutron star causing a companion star to explode as a supernova, thanks to data from the Very Large Array Sky Survey. Though there were earlier predictions, this was first noticed by scientists in 2017 when they found an object emitting radio waves, which had not appeared in an earlier VLA Sky Survey. Upon investigation, they found that the bright radio emission was coming from the outskirts of a dwarf star-forming galaxy, some 480 million light-years from Earth. The data gathered allowed the astronomers to put together the enthralling history of a centuries-long death dance between two massive stars that are more massive than the Sun. These two stars were born as a binary pair, closely orbiting each other, but one of them was more massive and completed its evolution earlier, exploding into a supernova and leaving behind either a black hole or a super-dense neutron star. Growing steadily, the black hole or neutron star's orbit entered the companion's atmosphere about 300 years ago, which led to the spraying of gas away into space from the companion. The ejected gas, spiraling outward, formed an expanding donut-shaped ring called a torus around the pair. Finally, the black hole or neutron star made its way inward to the companion star's core. This triggered a disruption in the nuclear fusion, producing the energy that kept the core from collapsing of its own gravity. And as the core collapsed, it briefly formed a disk of material closely orbiting the intruder, propelling a jet of material outwards from the disk at the speed of light, penetrating its way through the star, causing an early demise of the companion, turning it into a supernova. Upon investigation, it was also discovered that this was detected earlier in 2014 as a burst of X-rays coming from the object by an instrument aboard the International Space Station. The team has published a detailed article on this in journal Science, and according to lead researcher, all the pieces of this puzzle fit together to tell this amazing story, thanks to VLASS. That's not the only recent discovery in space. An international group of astronomers at NASA have made a new discovery contradicting the prevalent view about the aging of white dwarfs. White dwarfs are the slowly cooling stars which have cast off their outer layers during the last stages of their lives. Roughly 98% of all the stars in the universe will ultimately end up as white dwarfs, including our own Sun. However, this group of astronomers has found that white dwarfs can continue to burn hydrogen on their surface in the final stages of their lives to slow down their aging rate. To investigate this, the team compared cooling white dwarfs in two massive collections of stars, M3 and M13, which share many properties such as age and metallicity, the portion comprising other elements than hydrogen and helium. Using the Hubble telescope's WFC3, the team observed both these clusters at near ultraviolet wavelengths and compared around 700 white dwarfs. They discovered that M3 contained standard white dwarfs, which are simply cooling stellar cores, whereas M13 contained another type along with the standard ones. These other types were those which have managed to hold on to an outer envelope of hydrogen, allowing them to burn for longer and hence cool more slowly, which they calculated to be around 70%. This discovery could impact how astronomers measure the ages of stars in the Milky Way, as the standard white dwarf cooling rate is used as a natural clock to determine the ages of star clusters. Thus, this could mean that the estimates of the ages of stars could be inaccurate by as much as 1 billion years. To probe further, the team is now investigating other clusters similar to M13. Speaking of NASA's discoveries, the Hubble scope has captured a striking image of a rare celestial phenomenon called Herbig-Haro Object. Very specific circumstances form these objects. Newly formed stars, often very active, sometimes expel very narrow jets of rapidly moving ionized gas, which is so hot that its molecules and atoms have lost their electrons, making the gas highly charged. The streams of this gas then collide with the clouds of gas and dust surrounding the newly formed stars. It is this collision at speeds of hundreds of kilometers per second that creates the spectacular Herbig-Haro objects, such as this one. In addition, these are extremely difficult to observe, as though they release a lot of light at optical wavelengths, but their surrounding dust and gas absorb much of the visible light, making these observable only at infrared wavelengths. That's it for this week. Do let us know your thoughts on these spectacular discoveries and the episode, while we leave you with 3 captivating space images that are going viral on the internet.